Let's start by talking how to check assumptions for a multiple regression model. Now, what's interesting with multiple regression is it's a lot like simple regression, but we have multiple x's now. So you'll have the same conditions right here, linearity, as in we want a linear relationship within the model. But additionally, each x or predictor must have a linear relationship with y. This is when it works best. Remember, we're doing linear regression, so we want there to be a linear model, and for each x or predictor to have a linear relationship with the y. Additionally, we have the condition of equal spread. This means if you were to look at a residual plot, the points have equal spread around the line. So the equal spread means we have homoscedasticity, or sometimes called equal variance. So at all points around the model, we generally see a similar spread, not a differing spread, which would be non-equal spread. Additionally, we have the condition of normality of residuals. The normality of the residuals means that they follow a normal pattern. This will often be checked with a QQ plot for normality. This stands for a quantile-quantile plot. It's matching up the quantiles of the normal with the quantiles of your data, and that's where we get that line. That is not your linear model when we look at the plots. That is a line showing a one-to-one comparison of what we have in the normal and what we have with your data, and if it lines up one-to-one. So we'll see some of those graphs coming up here in a moment. But take a look right now. We have the pairs function, and the pairs function gives you a scatter plot matrix. Now, what you usually want to look at right here is the y variable of interest, salary, which is the thing we want to understand, and its relationship with each of the x's, which would be this top row across here. Because the top row has the y variable on the y-axis right here, and then each of the x's, spin away right there, each of the x's is going to be on the x-axis down below. So you ask yourself, is there a linear relationship? Experience seems to bend a little bit if we look through that plot. Some of them look to have linear relationships more than others. Now, we can use our eyes to check this out, or we can use p-values and use our eyes. We'll start off some p-values here in a moment. So now, reading the scatterplot matrix once again is looking at the y variable of interest with each of the x's to see if you see any evidence of non-linearity within the plots. The pairs function has the y variable first, and then we do tilde dot. That means y by x, and the dot means all your x's, comma data equals, and then the name of your data frame. You can also choose specific variables by going right here and using these square brackets to go all rows and then certain columns. So there's ways to restrict your columns to only look at certain x's if you're including them in your model. Now remember these steps. When you do a check regression, first thing you want to do is run check regression on the model and then see if all the p-values are greater than 0.05. And you might say low p-values are good. Well, low p-values just mean statistically significant. And in this instance, the null hypothesis is linearity is good, and then the other one would be equal spread is good, and then the other one would be normality of residuals is good. It's kind of an easier way of stating it. But with that in mind, if the p-value is low, we reject the null, and we would have evidence that linearity is bad. We'd have evidence that equal spread is bad, and we'd have evidence that normality of residuals is bad. So we want the p-value on the check regression, if we want to use our model, to be above 0.05. And if it is, we pass. Now, if it's below 0.05, we sometimes get a second chance to investigate this. If we have more than or equal to 25 values, we get the second chance to evaluate it. And to do this, we will look at the diagnostic plots. Think you're going to diagnose the issues and see how bad they are. But if it's less than a 25 sample size, we're just going to stop and we're going to say, these errors are too big, we're not going to use the model. So remember, start out by making your check regression, see if you fail any tests, p-values are below 0.05, and if you fail the test, see if you get the second chance by having a sample size greater than or equal to 25, and if that's the case, look at the diagnostic plots to figure out how bad the issues are. So check regression just takes our model right here. Your model is oftentimes stored into M, but sometimes we write M.1 or M.2 to denote a model like our first model, our second model, and so on. So you can call your model anything you want, but M usually stands for model, and it's quick to write. That's why we often use M. The linearity, remember, has the only real change right here, where we're going to look at the linearity for our model, and then additionally, the linearity with the y in each of the x's. So here is the new check regression output. The linearity for the overall model actually couldn't be performed. Duplicates, sometimes called replicates, are when a value of an x has repeated values. And that's how we can check if the line goes through the middle of it. Now, this doesn't mean we pass. It doesn't mean we fail. It just means the test couldn't be performed, which means we're going to have to look at the linearity for the overall model. So this is going to be a question mark. We really don't know what's going on right here. We didn't get a p-value to test it. It just couldn't mathematically be calculated. Over here, we pass this one because it's above 0.05. We pass this one. We pass, and we fail experience. Remember those plots you saw earlier? Experience is where we saw a little bit of a bend through the data. So now, since our sample size is greater than 25, we get that second chance right here. And let's go take a look at what's going on to see if we passed for the overall model and passed for the linearity of experience. We'd have to go back here to look at the linearity of experience in the pairs, but it also shows up when you run check regression. And notice how we do see a bend in the data. We're looking specifically at this plot because that is where salary and experience are. And there's a little bit of a bend, like if you were to draw through it. I don't know exactly what's going on right there. A little bit of issues. Give it a B-. I'd still let it pass. It's not the worst of issues I've seen. So we need to look at the residuals right here and see if there's any leftover variation that we haven't explained. Remember, your residuals should look random. A good residual plot will look random. It can have gaps right here because that's really not evidence of issues. It's just going to be, we don't know what's going on there. So we don't know if anything's bad is going on. It could be nothing at all. Additionally, sometimes people think this is a plot thinning, but if you have less data, it makes less scatter. So really not much is going on there either. We're looking for big issues like this right here. Clear evidence of nonlinearity, clear evidence of plot thickening, and then we have some nonlinearity slash, this one might have a little bit of plot thickening. We'll let the p-values decide that. Second one is linear, because the line slices through the middle of it, but then we have evidence of plot thickening or unequal spread right there. So that's a bit of an issue on the second plot. So these would be bad residual plots that we do not want to see. The QQ plot for normality is how we check to see if the residuals are normal. Do not check the normality with this plot over here, because this is only used for linearity and equal spread. The QQ plot for normality should generally follow the line. Now, if you have a little bit of issues, that's okay. This is probably an A-, and this also here has a little bit of an issue right there. That's probably an A- too. Hey, I'd be happy to get an A-. These aren't that bad of plots. So let's go ahead and check to see if there's any issues with our residuals right here and see if we have anything going on. Here we are with the plots, and we don't have to investigate all of them. Since we only failed for experience, this was the plot we were talking about. And it's a little hard to see, but there might be some bend through there. So maybe on the line going through the middle, I might give this a B-, because that line right there, is it really cutting through the middle of the data? Look how the points are more above it here, more below it there. We'll erase some of what we wrote. It's not the worst. It's not the best. It did okay. The other residual plots actually look very, very good. But here's a different data set with clear issues. And the issues on if we pass or fail the tests, well, now we fail all of them. We fail the linearity for each of the x and each of the x's, the overall model, the p-value for the equal spread, and we fail the normality of residuals, but we do get that second chance. So there's our second chance to investigate this, and let's take a look. Do we win out on this second chance? Here's all your x's. And if you notice, the nonlinearity of year made is also contributing to the nonlinearity of the whole model. The only one that I might give an A- to is the normality of residuals, and looks pretty good, but the equal spread is also flaring out right there, so it has a thickening to the model, so that's not good either. So overall, this is not a good model. I don't know about using it right here. I see major problems here. I'd give this an F. I'd give this an F for both, the equal spread and the linearity. And normality of residuals, not so bad. A-. I think that's that plot we saw earlier. But now let's hop to some other topics and talk about influential points leverage, and outliers. Continuing on, we have influential points, outliers, and extrapolation. So when we talk about outliers, influential points, and extrapolation, which of these points is going to be an outlier? Well, it depends on how we talk about it. If you think about this as height and weight, well, when we have height and weight combos could be somebody who is heavier than you would expect for their height, or somebody who weighs less than you would expect for their height, somebody who weighs a lot less than you would expect for their height, or somebody who's actually pretty close. If you look, that's the least outlier, because it depends on if we're talking about the univariate or bivariate sense. So an outlier is something that is unusual, but it has to be either in a univariate sense, like someone who's very tall, or it could be someone who's very tall but an unusual weight for their height. So outliers are things that do not follow the trend. Depends on if we're talking one variable or two variables. Because this individual right here has a very normal height, but they don't have a common height-weight combination that follows the trend in the data. The trend in the data can best be seen by doing a density ellipse around the data and seeing what is inside the trend. If you were to draw this out right here, the density ellipse goes with the line. And things that are further out, like these points here, are going to be more outliers than the rest because they don't follow the trend in the data. And that's the bivariate trend. So how can outliers impact regression? Outliers can do anything to regression. Anything. They can make the slope positive, they can make the slope negative, they can make the slope flat, they can do anything. They can make the p-values significant, they can make the p-values insignificant. That's why we often say QQ straight enough, no outliers, plot doesn't thicken. We don't want outliers in our regression lest they have an undue influence on the regression. So look at this right here. What is the influence of r squared? Well, without the point, there's an r squared of 0.85, and with the point, it goes to basically 0. Over here, there's a very low r squared, but then you add in the point, and there's a relationship. So clearly, they can impact r squared. Outliers can be hidden, though, because think about this. In the univariate sense, we're talking about something with an unusual height. That's easy to see. In the bivariate sense, it's unusual height-weight combination. We can probably see that. But what about if we go to 3, 4, 5, 6 variables? Now we're talking about an unusual combination of 6 variables. You have to think, what is an unusual combination of height, weight, GPA, distance from campus, friends on Facebook, all of these variables? And you're like, what would be an unusual combination? We would have a harder time understanding that, and we can't really detect them that easily by looking at their values. We would need something called leverage. So what is leverage? Well, leverage is going to measure this unusualness for us. And leverage is going to be how far something is away from the mean of the x's. So these are going to be the extreme values, things that are on the extremes. So think of somebody who is very unusual on every single characteristic, and they would have a lot of leverage on the model, and they're going to pull the model sometimes towards them. So over here, points would have leverage, and over here, points would have leverage. How about on this graphic? Well, if we talk about unusual, the most usual point is the mean of the x's, because now we're in the bivariate sense. So when we go further away right here, especially towards this point, that point is very unusual in its combination of x's, and it's going to have more leverage. So the more unusual you are in your combination of x's, the further you are away from the mean of the x's, the more leverage you would have. And now we have some examples of how leverage comes into play. The mean of the x's would be these blue lines I'm drawing right here, probably closer to. Let's put that one a little closer. There we go. Now, if you notice, only in one of these graphics does the line change with the addition of the red point. The second graphic shows a flat line that all of a sudden becomes sloped when the additional red point is added. Well, the third graphic right here has no leverage. But these graphics have leverage because the red point is far away from the mean of the x. It's just a simple linear regression in this model to show you what leverage looks like in one variable. So why is it not always influential? Well, leverage is one of the two components of being influential. So remember this, you must have leverage to be influential on the model. But the other key component you need to be influential on a model is to have a deleted studentized residual. Now that sounds complicated, but you've already heard of the idea of a residual. So what is a deleted studentized residual? Well, a deleted residual would say, delete this point, so we'd delete it, and then draw the line. If we did that, we'd have the black line right there. So the black line is the line without the point's influence. And then we figure out the residual from a line where it was deleted. So now we have a deleted residual. Its actual residual is smaller because it would influence the line towards it. The red shows the distance it is below the line, where the blue is the deleted residual, a line that does not have the influence because the point's been deleted, and then we find its residual from that line. But what is a studentized? Well, studentized is kind of the idea of standardized. Studentized is the student t-distribution. So we're actually turning these into t-scores. And for all intensive purposes, t's are just like z's. So a t-score is just like a z-score. So you think about your 68, 95, 99.7, t-scores kind of work the same way, especially with high degrees of freedom. They will converge towards z-scores. So whenever you think of studentized, just think of standardized. That means no matter how we measure the data, it's going to have the same context, which something outside of 2 and -2 is going to be unusual, because that would only happen about 5% of the time due to random chance. So here we are with our definitions of what is unusual. We will compute large leverage by this equation right here. And an unusual deleted studentized residual is going to be outside of 2 and -2. So we can then graph this and see if anything is unusual using what is called an influence plot. Influence plots look for influential points and then mark those points and tell you what rows they're in. So here we are with our influence plot. This line right here is where high leverage is. So to be influential, you need high leverage. So you must be to the right of that line right there. But then we have the other characteristic, which is a large deleted studentized residual, which is outside of this. And that's going to be large deleted studentized residual. So if you are outside of these bounds right here, you have a large deleted studentized residual. So with that in mind, there are no dots that fall into the quadrants you see where you would have a large deleted studentized residual and large leverage. Those are the quadrants right there where points would have undue influence or large influence on the model. If you notice, the size of the circle is the size of the influence. Points that are right near the center, where the line would be, down this way, we'll use a different color, are points that don't have a large studentized residual, deleted studentized residual, so they're very small. But what about where we do have influential points? Notice how the biggest circle is the one with the biggest influence, and the influential row is row 39. It falls into one of the two quadrants with a large influence because it has large leverage and large deleted studentized residual. You can often get more rows right here, and notice how we have a lot of our largest circles here. And you could also technically investigate some of these circles, which were not returned because they don't have an X in it, telling you that they're one of the returns up here of the rows with undue influence. So it is possible to go beyond this and find additional rows and actually quantify, as we do, the amount of influence they have. But we often just look at the influence plot to see if we have any highly influential points and then investigate these rows. So now that we know the row numbers, we can take the row numbers with undue influence or too much pull on our model and return them the following way. Notice how it says data 43. Well, if you just put your row numbers inside of there, you will get those rows and you can look at them to see what's going on and why they have so much influence on your model. Extrapolation is the same thing in the multivariate world as it was in the simple world. But the issue is, now we're dealing with multiple x's. So when are we outside the bounds of our x's? Well, it's hard to tell, and it's hard to know when we can make good predictions. Because when we use this model up here to make predictions, the further we are away on our x's from the mean of our x's, the more we're extrapolating the model. But what if we're outside on one X and inside on another X? That can happen. So we need some way to know if our predictions are reliable and if we are able to make good intervals that we should trust. So how will we possibly do that? Well, we'll need to check to what degree we're extrapolating and if the combination of our x's are very unusual and things we wouldn't see. To do this, we are going to do the extrapolation check to see how unusual our x's are. Notice this is the pattern of the x's right here. So this x right here, or that dot, has an unusual combination of x1 and x2. So to predict for that, it would require the greatest degree of extrapolation. But there could be more dots, new data that's even further away. And if you think about this as a density ellipse going out further, that dot over here would require the greatest amount of extrapolation. So the further you are away from the mean of the x's, which would be right inside of here, the more extrapolating you have to do to use your model to predict. We don't have to figure this out on our own. We have the function extrapolation check. What does extrapolation check do? It checks how much you're extrapolating. So what we'll need to do is put in the combination of points. We'll put in the values of this point. Maybe that is x1 at 21.5 and x2 at 32.5. And what we would find out is that point right there requires the most extrapolation. Drawing out the density cloud, it would be the furthest point away if you notice as you think about the points going out in a density. And here's the return we get. That point that I talked about right there is at the 100th percentile. That means it has the most extreme combination of x's. So it requires the most extrapolation. This point right here, point 1, is going to be the one that requires the least extrapolation. See if you can see that on the screen right here. The point that requires the least extrapolation would be this one right here. So that's point 1. This one requires a good bit, and this one requires the extreme. And there they are in the return, telling you how much extrapolation from point 1, point 2 to point 3, and the percentile by which you'd have to go through the data to predict for them. You do not want to be generally above 90, 95. You get towards 100, that's really bad. Because that means you're so far out on the x's, you don't have any data. If we had a point that was directly at the center, it would have a percentile of 0. Because you don't have to go through the data to get to it. It's where your model has the most understanding. So the lower the numbers on the extrapolation check, the more reliable your predictions are, and the less extrapolation you have to do.